In this podcast, you're going to see a few examples that detail how you can find local maximum and or minimum, as well as absolute maximum and or minimum points for a variety of different functions. We'll focus on some simple polynomial functions, but what you see here in this video will apply to all of the functions that one could study. So if you look at the lesson objectives before you, we're going to bypass number 1 to some degree. I know that we can graph, and I know that if we needed to validate or check an answer by using technology, we can. And I will introduce some of the terms and set the stage for the calculus by looking at a graphical interpretation of finding minimum and maximum values. What you can do from there is you're welcome to sketch them down. You're welcome to print off some of the lesson notes and incorporate them into to your own notes. But the note taking, or the majority of the note taking, should occur when we get to finding the max and min values of a function using calculus, which is objective number 2. You'll find that I'm not going to pause throughout the video. I'll allow you to do that at critical moments where you feel you need to take information down and to record some questions that you might want to bring back to class to ask. So here we go. Let's consider the following quadratic function, y equals x squared minus 6x plus 10. Now you and I both know very well that the graph opens upwards, so that would mean that the function has a minimum value. In fact, the function not only has a minimum, but it has an absolute minimum, because all of the surrounding y values, that is the values surrounding the vertex, are going to be greater than the y value of the vertex. So let's take a look at the graph of that function. So in using notebook software, we can attach the graph or the function to its graph, and it actually has a extrema finding feature called find extrema. So the result that it says is that there is no max values, meaning that there is no maximum, but rather that there is a minimum value in this case. So just to make this clear, the program refers to this as its y value. Okay, so according to the graph, we have a absolute minimum at 3, 1. So again, 3, 1, okay, represents an absolute minimum. Okay, so 3, 1 right here, an absolute minimum. And its minimum value is 1. So if we want to write some form of definition for an absolute minimum, what we could say is that in general, let's take note of this right now. So an absolute minimum, I'm just going to be brief here, an absolute minimum occurs at an arbitrary value, call it whatever letter you like, just not x or y in this case. So let's just say that at x equals a, let's go with that, if the value of the function at that specific value of a is always less than or equal to f at x. Okay, so f at x meaning any y value, other y value, just not the one that happens at x equals a. So if f at a is less than or equal to f at x for all x within the domain of the function. So there's an absolute minimum. In the next one, you can see that it is also quadratic, and due to the leading negative coefficient, that this function is going to have an absolute maximum. So let's just quickly look at the graph of that. So in terms of its extrema, there's no min, but there is a maximum y value. So we have an absolute max here, okay? And that occurs by definition. So it occurs dot 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 when at some arbitrary value of x, call it a, when at x equals a, the value of the function at a is going to be greater than or equal to all other values of x along its domain. Okay, so there are two types of the extrema, an absolute minimum and an absolute maximum. Now we'll get into a different class of functions. So have a look at this one. We can see it has a positive lead coefficient of 1. We can also see that the degree of the function is 3. So we can probably appreciate the shape or the quadrant flow of this graph. That is starting down here in quadrant 3 and ending up in quadrant 1 with 2 turning points at most and 3 zeros. So let's go ahead and graph this one. You're welcome to use your own technology and study where its extrema happen to be. But upon graphing, you're going to see that the extrema are just a little bit different in this case. We actually have 2 of them. Okay, we have this one here at 2 minus 2. And we have another one at 0, 2. So if you take a look at 0 and 2, that would give us this value here. This one is referred to as a local or relative maximum. Okay, whereas the other value at 2 minus 2 is referred to as a local or relative minimum. Now it's all fine and good to say that these values occur here because I have a graph in front of me, but it is entirely a different thing if we do not have graphing technology, or we're expected to determine where these values are algebraically. So the way to get around that is by working with the function's derivative. So if we derive this function from here, okay, so this would be your dy by dx. By deriving that function, take a look at its graph. Okay, and what I want you to focus on, let's just move this out of the way for now. Let's focus on this point here. That is to say the local maximum. That local max is occurring at a position where the derivative function flows or moves from having positive y values to 0, then to negative y values. Okay. Now focus on the local minimum, which is here. What you can see is that at the local minimum, we start off with negative y values. We hit a 0 for the derivative, and then we end up with positive y values. So you can kind of see that at the local minimum, the values at x equal 2 change from negative to 0 to positive. Whereas for the local maximum, which occurs at x equals 0, we can see that the values change from positive to 0 to negative. Okay, so that is flowing in this direction and this one going this way. So there's something to be said about this, that if we need to find the positions of local extremes, local maxes and local mins, then we simply need to analyze the derivative function for where it happens to change sign. Where does it go from plus to negative or from negative to positive? Okay, so what we're going to do is we're not going to formally define in words using notation like we had done for the absolutes, but I do want you to know that the visual you have in front of you is a way of defining how to find those local maxes and the local mins. Okay, another thing that you do need to recall and take note of is the fact that, let's get a different color out here, let's go with orange, is that when we're talking about local mins or local maxes, we really are referring to the turning points of the function. Okay? All right, let's move on. So with this one here, we have a quartic function, positive lead coefficient, even degree. We know that the graph itself is more than likely going to have some form of W shape to it. And with that being said, we could probably appreciate that there will be a local extreme here, so a local max, and that either one of these could be an absolute max and a local minimum. Okay, so we'd have to use graphical technology to interpret that, and later on we'll use algebraic techniques as well to determine that. Let's take a look at its graph. So here we have some extrema. Okay, so we have 3 of them, in fact. So we have here a local min, right? Because if we were to graph the derivative function to this, what we would see is that the derivative would 0 here, and it would go, oops, sorry, just revise that idea here for a second. It might be best if we actually graph the derivative function. And I think I'm going to come back and do that in just a moment. We have a local max, and we have an absolute min. Okay, to which we will have ways of determining the nature of their extremes, whether they're locals or absolutes. Let's take a look at, let's get another equation down here. Let's go with the derivative of that. So y equals, so we would have 12x to the power of 3. So a cubic function. So I just want to make clear that concept of tracing out the local mins and maxes and then multiply that by 12. So subtract 12x squared. And from that, we'll subtract 12. Let's double check we have that correct. Now, equation editor had blocked out a part of that on me, so that should be a 24 on the end. And a 24x with a constant of 2. So if we were to graph this, let's take a look at that idea. Okay, so earlier on I did place a point here. So we can see how with the red graph, which is the derivative, this is our derivative graph, the red one, that's our dy by dx, our dy by dx. We are moving from negative values through to 0 to positives. Again, the same thing happens over here, is at this 0 to the derivative function, we can see we have a local maximum as we are moving from positive to 0 and then to negative y values. Something else to note too is that at each of these particular values, specifically this one down here, where all extremes, we know that the tangents or the slopes of the tangents there are 0, which is a technique you'll see shortly for finding out where these extrema occur. Now let's move on. We're going to check our running time here on our video, and we're now at 15 minutes, so we should be close with the next 5 to 10, and we'll max out at 25. So we're going to determine the min and max values using calculus for this one. So based on this function, what we'll do, of course you have to pause the video as we move forward, is we'll take the first derivative of the function. So we have a linear function of 2x minus 6, and then what we'll do after that is we're going to determine the slope of the tangent to the line at the min-max point. And at those points, as just mentioned, that the slope is 0. So f prime and x is set equal to 0. So what we'll do is we'll determine the x value that satisfies that equation, which is none other than x equals 3. So what we expect is that we're going to see, in this case, this was the original or opening function to the lesson, that we had a graph of a function opening upwards. So we can expect that the vertex would be at 3 comma some y value. In fact, it would be a minimum value. You do have algebraic techniques for determining that. So what we're going to do, let me just backtrack a bit here, make sure I've covered all my bases, is to substitute it into the original function equation, and then to determine, and this should give us a value of 1. Let's just double check here and see. We have 9 minus 18 plus 10, which yes does give us 1. So it validates the graphical approach on the very first slide of the lesson. So we know that this function has an absolute minimum at 3 comma 1. Now let's just say, for instance, we didn't have any knowledge of what the function's characteristics were. We had the function equation, we knew how to find derivatives, we knew about slopes of tangents, and if they're horizontal, then we know that at those x values we're going to have a min or a max. So if we want to rely on an algebraic technique, then for finding mins and maxes, what we'll do is we'll find the second derivative, okay? Because with the second derivative, okay, if it is positive, the function has a minimum. If it is negative, it has a max. So what this implies here is that the ordered pair 3, 1 is a minimum, right? Since f double prime at x is positive. So what that means is we're now at a point where we can use calculus to validate the other two. And this is where the lesson is going to end. Okay? So let's model one of these. You can very well go ahead and practice the other. We'll do the first one. This one here, just to let you know. Let's undo that change. As you work your way through, you should notice that these same points came up earlier in the lesson in the graphical approach. But what I would like you to do is to determine, using calculus, where the max and mins are, and then to determine using other techniques involving the derivative, if you would classify those as local or absolutes. So let's look at the one at the top. So using calculus, we'll find our first derivative, dy by dx, and that's going to give us minus 8x plus 4. Okay, so what we would like to do is for that parabola opening downwards is to find its absolute max. So what we'll do is we're going to determine where, okay, we want to solve dy by dx, okay, equal to 0. So where's the slope of the tangent 0? Well, it would be at that turning point or at the function's vertex. So by setting that equal to 0 and solving, we are going to determine that 0.5, right? 0.5 is going to be the value that does that for us. If we then evaluate the function y at this x value, so let's go ahead and do that. So we'll take a quarter of minus 4 and get negative 1. To that, we're going to add half of 4, which is 2, and then 13. So it looks as though we have 14. So let's just verify this again. So square of 0.5, we have a quarter of 4, negative 1, add on half 4, which is 2, and 14 is the final answer. Therefore, we know that the ordered pair 0.5 comma 14 represents an extreme point. With y equal 14, an extreme value. Okay, now given the nature of the function being quadratic and opening downwards, we know that it only has the 1 and that it is an absolute. But whether it's a max or min depends on the sign of the second derivative. Okay, so let's go ahead and figure that out. So f prime, but if I'm going to use Leibniz notation, then the second derivative is d2y over dx squared. And there's a reasoning behind that. The reasoning is given because we are taking the derivative of dy by dx, right? The derivative of the first function with respect to x. So if we do work that out, we'll end up with d2y, d squared y by dx squared. So let's look at the second derivative. So recall that here is our first derivative, and if we find the derivative there, we end up with minus 8. So since the second derivative with respect to x is negative, okay, has a negative value, then the function y has a maximum. So specifically, therefore, 0.5 comma 14 is a maximum. Okay, so please take your time to review any of the concepts as necessary. If you have any questions about what's been presented, please bring them forward in tomorrow's class. And then you'll spend the majority of your time applying these concepts to solving some applications and to do some problem solving.